So, welcome everyone. Today we're going to have the fourth and the fifth lectures of this Cavalier summer program. The first lecture is Michel Rieutord. This is his second lecture so far. Michel is a professor of physics and astrophysics at Paul Sabatier Toulouse III University. He's a specialist in astrophysical fluid dynamics with a special interest in rotating fluids. In the last years, he has developed with his team advanced models of rotating stars, and he's leading the ESTER project. And that's all I wanted to say. So it's all you, Michel.
And start. So yesterday we stopped the end of the local analysis that I used for dealing with waves and perturbations in the general sense of fluid flows. And I just want to recall the fact that so this approach is quite simple in the sense that we don't have any differential equation to solve. It can reveal the potential mechanism of instability if we find, thanks to the dispersion relation, some region where for instance, the frequency is complex. But of course, there are drawbacks, and that's there is a price to pay for this simplicity. Is that this is local, and we cannot deal with boundary conditions. And neither we can deal with the variations in the background. And for that, we need to assume that the wavelength is always much smaller than the scales of the background. Here I write the velocity over which the scale over which the velocity would vary. But that could be any quantity which is defining the background, like the density or the temperature field, etc. So if we are in this situation where we cannot use this local analysis, then we have to deal with boundary conditions. And of course, the problem becomes much more complicated in the sense that we have to determine this the spatial structure of the waves, which we call now modes or eigenmodes. In fact, these functions, functions of the spatial coordinates, are the eigenfunctions of an eigenvalue problem, which looks like this. In fact, we just impose the time dependence as an exponential dependence. So in fact, where we can separate the time variability and the space variability. But in general, this eigenvalue problem is a little bit more complicated in the sense that it is a generalized eigenvalue problem with two operators. So L of V, for instance, is equal lambda, another operator applied to the velocity field, or actually any field which comes into this problem. Yes, why this is in the general case for this generalized eigenvalue problem is that, for instance, just think that you take the curl of the momentum equation so as to eliminate the pressure. And in this sense, you already have an operator here. This is the curl operator, which is there in that case. Okay, so this is indeed a very difficult problem. And to make progress, we usually simplify this big problem. And one way to simplify this is to combine this global analysis with local analysis in the direction where you have some homogeneity, in the sense that, well, the background does not vary, or you don't have any boundary conditions. So, for instance, if you have a periodic container, if you have a sphere, for instance, I will give immediately an example, a simple example with a fluid which is contained between two cylinders here, and which is rotating at some arbitrary angular velocity depending on the radius, which I call S here. And what we will see is how we can analyze this thing. So let's go and write the equations. So I assume that the fluid is also incompressible, so that I simplify at the maximum. So the little u is the perturbation, the capital U is the background flow, and this background flow is just a rotation rate, rotating flow, but with some differential rotation, which is arbitrary and which depends on the problem at hand. So the eigenvalue problem generates, if you insert the time dependence, then you get this this equation. Oh yes, sorry, I'm a bit confused. Yes, so if you just express this form of the background flow, then you get something like this, this vectorial equation, which you can manipulate, and this is what I will show you now. But so the first step that you would like to do is to solve completely this problem. If you want to solve this problem completely, you see that you have an homogeneity or periodicity in the phi direction, in the azimuthal direction. So you can use a Fourier dependence for this variable. So that simplifies the thing. But for the radial and the z direction, you don't know anything. You have to solve the full partial differential equations. So that's if the cylinder is of finite length. So if you impose boundary conditions on the top and bottom of the cylinder. So one way to simplify is to say, okay, no boundary condition in Z, you take an infinitely long cylinder. Another simplification is to say, okay, no dependence of the perturbations in the phi direction. So I restrict both the background flow and the set of perturbations that I allow to this flow. Of course, doing this, I will not get the complete solution. I will just get a partial answer to the questions I'm wondering about. For instance, whether this flow is stable or not. So let's do that. And so you report, so you see that you remove the z from the unknown function and you put it as a Fourier dependence. And then you put this in the equation and you get, so the three equations of the momentum, the mass conservation equation, and here I introduce this quantity phi1, which you see is the derivative of s squared times the angular velocity. And in fact, if you think a little bit about this physical significance of this quantity, it's just the angular momentum, the local angular momentum per unit mass. So in fact, this quantity is its derivative. And so you can manipulate these four equations and reduce them into a single one for the radial velocity of the perturbation, and you get a problem like this, a second order differential equation with boundary conditions, where you impose that on the walls, the radial velocity is 0, and you have this quantity function of phi1, which is also called the epicyclic frequency, and which is related to this derivative of the angular momentum. Actually, this frequency is the analogous of the Brand-Weisele frequency for a stably stratified fluid. Here, it's a stratification in the angular momentum, actually. So let's continue. So the point now would be to solve this problem, this eigenvalue problem, to determine this the eigenvalue lambda and the associated eigenfunctions, and see whether we have unstable modes for this situation. In fact, we can avoid this painful solution, because this problem belongs to a class of general problem which are called the Sturm-Liouville problems. This is determined by the structure of the differential rotation, and so that's we are using a mathematical result which says that in fact the eigenvalue of this problem, so this big lambda, this capital lambda, which is the inverse of the square little lambda of the eigenvalue, the original eigenvalue. These eigenvalues, they are real and they are discrete. So you can make one-to-one correspondence with numbers. What the mathematics say is that if this function remains positive in the whole interval where the fluid is, and where this function is defined, then all these eigenvalues are negative, discrete and negative, and they go to minus infinity. And in that case, since you have to take the square root of the inverse of this quantity, of this negative quantity, you find that, in fact, the original eigenvalues, they are just pure imaginary numbers, which means that the waves actually are just oscillating without growth, without damping. But without damping, this is natural, since we just removed any dissipative mechanism. However, the properties of this Sturm-Liouville problem also says that if somewhere this function here in this second operator is negative somewhere, then there are positive eigenvalues in the spectrum of this operator. And therefore, in that case, the flow is unstable. And this is the substance of the Rayleigh criterion, which says that if in fact, the angular momentum is increasing outwards with a growing radius, then the flow is stable. And if in some place it decreases, then you have an instability. In fact, I'm exaggerating a little bit, because, as you know, the perturbations that I have considered are only axisymmetric perturbations. So the only thing that I can say, actually, is that if somewhere the angular momentum is decreasing, then the flow is unstable. Then there are axisymmetric perturbations that can grow and destabilize the flow. If phi is positive, I can say that all the axisymmetric perturbations are stable, but there might be non-axisymmetric perturbations that may be unstable, that may be growing. But this we can't say, because we have simplified the problem. So that's just an illustration of how to deal with these global problems, where you have to take into account the boundary conditions, or, as here also, the inhomogeneity in one direction. So now let's talk a little bit about stars, because this is what we are here for. So in stars there are many waves, because stars are in fact quite complicated objects. First, let me derive what are the equations which govern these perturbations in a star. So I will take all the equations, and first, of course, the mass conservations, and I perturb this and get this equation where you have, you see that the background, rho 0 is now not constant. I just keep it inside the divergence. So this is the mass flux, divergence of the mass flux. Then the momentum equation, here I simplified it as by considering an inviscid fluid. So what is new here is that you have also, well, in a star you are feeling gravity. It's a self-gravitating fluid, so the gravitational potential may be perturbed by perturbations. I have linearized this equation, all these equations, of course. Then you have to consider the problem of the entropy. And here also I simplified the problem with removing the heat diffusion and therefore considering just adiabatic perturbations. So you get this simple equation for the perturbation of entropy. Yes, for those who are familiar with these perturbation analysis, I'm considering Eulerian perturbations, not Lagrangian one. Maybe I can come to that with the questions if necessary. Then, of course, you have an equation for the self-gravity. So the gravitational potential is related, its perturbations are related to perturbations of rho, of the density. Then you need the equation of state, where here I could have simplified this a little bit because since I'm considering isentropic perturbations, then you just need the perturbation of with respect to rho at constant entropy. And then, of course, you have to take into account boundary conditions. And usually for such adiabatic perturbations, you just impose no pressure perturbation at the surface, and you have to match the gravitational potential with that in the vacuum. And in 1D, this is very easy conditions. But sometimes people simplify the problem in neglecting this perturbation in the gravitational potential. But so that's called the Cowling approximation. It does not complicate the things so much, so usually it's taken into account. So let me talk a little bit about acoustic modes. And some recent results that have been obtained actually in my group here in Toulouse by my colleague François Lignière and his students and colleague Bertrand Georgeot and students and postdocs. We were interested in the problem of acoustic waves and acoustic modes in rotating stars. And the problem with rotating stars, and especially rapidly rotating stars, is that they are no longer spherically symmetric. And if they are not spherically symmetric, then you lose the possibility to separate the variables. If the star is actually spherically symmetric, the modes, in fact, are just of one type. There are these, what we call the whispering gallery modes, where the waves you see is just bouncing on the surface and being refracted at some depth. Some might go to the center. No, it's not a problem. And these modes and waves can have the radial structure and angular structure separated, and therefore the differential equation that you have to solve is just an ordinary differential equation. When the star is flattened by centrifugal effect, then you have new kinds of modes which come into play, and my colleagues have studied actually the dynamics of the rays which are associated with these acoustic modes. So these are acoustic rays, And you can study them just as a dynamical system. And in the middle of this picture, you see a Poincaré section. So where you have here theta, which is the angle where the ray is bouncing on the boundary, and here the wave number in this theta direction. So a sort of velocity component. So what is important here is that you see three kinds of modes which appear. In fact, you have these little islands here which are representative of these whispering gallery modes and which are associated with periodic orbits. You just think of particles just bouncing in this potential. But the new modes, the new thing is that you have new periodic orbits, which we call the island modes, because they remain in a sort of island in the middle of the chaos of other rays. And this corresponds to rays which are bouncing here between two latitudes and which do not visit the center, just like the whispering gallery modes. And everywhere else, at least in this region, you have these chaotic rays, which are associated with chaotic, eigenfunctions, which we call chaotic modes. And all this is very similar to what has been studied in quantum mechanics by people who were interested in quantum chaos, which is this very same problem where you have a classical particle which in some potential has a chaotic trajectory. And the question is, what is the shape and what are the properties of the wave function, of the probability density of this particle in such a well, and what are for instance, the levels of energy, etc. Here, for the stars, the problem is to see what is the structure of the spectrum and how the frequencies of these new acoustic modes are distributed in the range of the acoustic frequencies. And of course, one thing which would be interesting is to identify such modes and have new informations on the properties of the stars where the rays are propagating. So just to complete this picture, these are the little zoo of these acoustic modes. So you see here the island modes, which are so focused along the trajectory of the associated acoustic rays. The chaotic mode, so well, you see an eigenfunctions which more or less visit all the star, and the whispering gallery mode here, which is confined near the surface. Of course, all these modes are not not the same visibility, because here you have a lot of oscillation at the surface, and when you observe a star, you won't see such mode because it's because there are compensation in these bright and dark and bright and dark, so it does not make strong fluctuations. But island modes, I think, can be visible modes, and maybe there is also some suspicion for the chaotic modes. So the question I would like also to discuss a little bit is, how can we destabilize acoustic modes in a star? And give you a brief introduction to what is called the kappa mechanism. So I take here the most simple, the simplest situation, where I assume that the background of the star is isentropic. So just imagine a star which would be completely convective, but you forget about turbulence, which is driven by this convection. So and I also neglect, as you can see, the fluctuation of buoyancy. So I neglect gravity. So really, this is something very, very simple. But I just keep the essence of this mechanism. So what I will do is just use again the local approximation and assume that I have plane waves which propagate in such a medium. And I first assume also that the conductivity, the heat conductivity, chi here, is constant. And I assume this dependence of the perturbations. So you assume that chi is constant, then you differentiate this, and so the only thing which can vary is the temperature, and so the divergence of the heat flux is just for a plane wave minus k square times the conductivity times the temperature perturbation. And if you eliminate everything, then you get the dispersion relation, which I write here. Recall that lambda is complex here. It's not just the pure frequency. It's the complex eigenvalue. It's not really an eigenvalue here. It's or is it? No, it's just the complex frequency. The coefficients here, you can see tau here. Tau is k squared times kappa d, and kappa d is the diffusivity of the gas. So it's the conductivity divided by the density, and Cp, the heat. I don't know in English, what is it? The heat capacity, yes. Well, it comes back. So this tau, in fact, is the diffusion time scale, which is associated with the scale, with the wavelength, so with 1/k. So that's basically this. Omega here, which comes up, is the frequency of the wave. So it's the wave velocity times k, times the wave number. And gamma is just the adiabatic index, which I write as a function of the polytropic index n. So now I solve this equation, this third order equation, in the limit of a small damping rate, because here I assume I have just diffusion, so I expect that the waves are damped. And if you assume this, you immediately see that these two quantities, if you take lambda equal minus tau, these two terms compensate, and these two other terms, they are of order tau to the cube, so they are very small compared to the two others, so we can neglect them. So in the first approximation, we have just a single root, which is lambda equal minus tau. And once you know this root, then you can factorize the equation and get the two other roots, where you see that they are associated with the oscillation, the acoustic oscillation, but with a damping rate, which is again this tau, but here divided by 2n, and is the polytropic index. Okay, so this is just for showing you that, as expected, if you have a dissipative process, then you are damping the waves. So the point now is what happens if this quantity, the heat diffusion, the diffusivity, is not constant, and if I have this more complete equation where the heat conductivity depends on the temperature. In that case, if you do the perturbation analysis, then you get this quite big equation, quite big term here, with the derivatives of the conductivity with respect to temperature, and where the background temperature field comes into play, and you have complex things. So In fact, the game here is to see a situation where this term, which is, you see, negative when all these are 0, if this term between the square brackets can be positive in some place in the star. And in this case, we can hope that the waves are destabilized. At least they are amplified in this region. So this is what I have done here. I have written again this equation, and I have factorized -τ here. And what I would like to know is when the term in between the square bracket can be negative, so that I have a positive, a negative damping rate or a growth rate, simply. So the first thing I will consider is the case where the conductivity decreases with temperature. And actually, this is typical of partial ionization of region where you have this partial ionization of hydrogen or helium. In fact, this is not a usual behavior of the conductivity, because if you consider the conductivity of the air, for instance, here in the room, if the temperature rises, then the conductivity rises, actually, because you must remember that the conductivity is proportional to the diffusivity. And the diffusivity is the product of the velocity of the particles, so the air molecules, times the mean free path. So if you increase the temperature, well, the mean free path doesn't change much, but the velocity of the particles increases. And if it increases, then the diffusivity increases and the conductivity of the gas increases. So that's the usual behavior. But in stars, you have places where the hydrogen and helium are partially ionized. And when you increase the temperature, what happens is that this hydrogen or helium, they free their electrons. And so you have more electrons in the medium. And as you know, electrons, they are charged particles, and they interact very strongly with electromagnetic waves. And of course, one thing to know is that in stars, since this is a very hot medium, the conductivity is essentially that realized by the photons, by light, and not by the collisions between the particles. It's the photons which are supporting the heat flow. So if the photons can't go through the matter, then there are some difficulties. And so if you liberate a lot of electrons in the medium, then you make the medium more opaque and less conductive as far as heat is concerned. So let's consider that we are in such a situation where if you increase the temperature, the conductivity decreases. The next thing is to see that the background temperature, the Laplacian of the background temperature is always negative. And this is easy to see, actually, because I have made this little drawing. You see that the temperature is just monotonically decreasing from the center to the surface of the star. So if you multiply by R, then you have a function which is like this. And such a function is just like a parabola with negative x squared. You can see that this function is growing first, so its derivative is positive, and then it's decreasing, so the derivative is negative. So the derivative is first positive and then negative, so it's decreasing. So it's the derivative of the derivative is negative, is decreasing. So this is why this quantity is always negative. And what you see here is that we have a positive term which can compensate, presumably, the unity here. Now there is the question of this term, this other real term. I won't consider these terms. You see, these terms are purely imaginary, so their effect won't be will be just to modify the frequency and not the damping rate or the growth rate. So we have just to consider these two terms. So let's have a look to the other term. So since this one is positive, so here, oh yes, I should have written this before, but this is the expression of the conductivity as a function of the opacity here. So you see that if medium is opaque, so opacity is high, then conductivity is low. And that's the thing to remember. So let's assume that, for instance, the opacity is varying as t to the power minus beta. This is what you find, for instance, in the Kramer's opacities. This is so beta is sort of the logarithmic derivative of the opacity with respect to temperature. So the conductivity is behaving like this. So to the temperature to the power beta plus 3. So its derivative is in this shape, and its second derivative is so beta plus 3 times beta plus 2 times the temperature to the power beta plus 1. So if chi prime is negative, so if the conductivity is decreasing with temperature, then we have to have beta less than minus 3. And if it is less than minus 3, it is less than minus 2. So this term, this product is positive. And so this quantity, which comes from this, this term here, is also positive. So if now these two terms, this one and this one, are positive enough, and this is actually the case, you can have a negative damping rate, so a growth rate, and the acoustic waves in the stars can be amplified. And this is the basis of the kappa mechanism, which can destabilize the acoustic waves. Now let's talk a little bit about internal gravity waves. I have shown you these waves in the SF6 mixture with air. So you see that these waves, they exist when you have a stable stratification of the fluid. I have written here the perturbation equations, and I'm using here the Boussinesq equation. The Boussinesq equation means that I'm considering the fluid as an incompressible fluid. So you see that the divergence of V is 0. So this is an approximation of reality, of course, and it wouldn't work in the whole star, but it works nicely if the medium you are considering has a constant gradient of temperature, that the velocities that you are considering are much less than the sound speed. Yes, I can't read. Which is important when you are dealing with convection. What else? In one word, in fact, what is important is that the fluctuation of density are important only here in the buoyancy, and nowhere else. In fact, you don't need to consider them here, for instance. So you also consider that the temperature, the density fluctuation just depends on the temperature fluctuation. And this is a consequence of these approximations. This is, you can have a look to the books, and this is detailed there. So let's consider a situation like this, where you have a layer, which which is uniformly stratified, so the temperature or the entropy is just growing steadily with height. And so since I'm considering the Boussinesq approximation, that means that I'm considering the temperature. And so I will consider the temperature, the background temperature growing like beta z. So beta is the temperature gradient. And I assume that the background is at 0 velocity. Yes, because here I have written this with a non-zero velocity background, but that's for future, for the third lecture. Okay, so let's derive first the dispersion relation, as usual. So you see here the momentum equation, the equation for the temperature fluctuation, and the mass conservation continuity equation. One point is, yes, you see that here the waves are necessarily transverse. It means that the velocity of the wave, of the oscillation, is always perpendicular to the wave vector. So if the wave is propagating in one direction, the oscillation is in the direction perpendicular to that. So what we find, eliminating the amplitudes, we find the relation between the frequency and the wave numbers. And the novelty here is that this frequency depends on the direction of propagation of the wave. And you see you have this quantity which appears. This is n, and this is the Brent-Weisele frequency, which is so related in our in my setup. This is related to beta, so the temperature gradient, alpha, which is the dilation coefficient. And more generally, you can see this as the scalar product between the gravity and the entropy gradient divided by Cp. So that's n squared. And you see that if these two vectors are parallel, then n squared is positive. So you have a stable situation. So the one property of these waves is that they are anisotropic, as I said. So the frequency depends on the direction of propagation. And also they are purely 2D in the sense that the motion is in a plane. If you assume that ky is 0, then vy is 0. And this is immediately seen on this, on the momentum equation, because you see that if you set ky equals 0, this has no y component, and so vy is 0. So in fact, the motion of these waves is in a plane. Another property is that the group velocity, which is the gradient in the spectral space of the frequency, is perpendicular to the phase velocity. So you see it has this expression. Well, you can derive this. And you see that the scalar product of the group velocity with k is 0. So in fact, the energy is propagating in one direction perpendicular to the phase direction. And that makes the behavior of this wave quite weird, so to speak. It's quite bizarre and unexpected. And I will come back on that. But before I come back on that, I would like to say just a few words for the moment on the modes which are associated with the gravity waves, namely the functions which appears if you do not assume a Fourier structure. So if the spatial structure is arbitrary. So I just assume that the time evolution is periodic. I still assume Boussinesq approximation. And so what I do here is I take the divergence of the momentum equation. So I eliminate this term and you get the Laplacian of the pressure perturbation equal to this, the divergence of this term. And you can eliminate then the temperature fluctuation using the equation of temperature. And what you get is this partial differential equation, which is called the Poincaré equation, and which I have here explicitly written with all the coordinates. And this equation has something special, which is it is hyperbolic in the spatial coordinates. It is hyperbolic because here, this term, you see, the coefficient of the derivative, the second derivative with respect to z, to z, is negative. I will come back on that. And before, I will discuss now the inertial waves, which are the waves associated with Coriolis force, so with the rotation. In fact, these waves exist because in a solid body, the distribution of angular momentum is growing outwards, like I've said when I discussed the cylinder. So we are in a stable situation as far as the Rayleigh criterion is concerned. And so this gradient of angular momentum acts like a restoring force. And in fact, this is the job of the Coriolis force. So I have written here the Navier-Stokes equation in a rotating frame. I have scaled the quantities with, using this time scale, so the rotation of the background, and some arbitrary length scale, and the velocity scale in the rotating frame. So what you see here is that you have two numbers. I won't discuss them very much. The Rossby number and the Ekman number, which Matt has discussed. And what is important here is to notice that if the fluid is dominated by rotation, then this velocity, the local velocity, is very small compared to the background velocity. And this is equivalent to saying that the Rossby number is very small. And the nice thing is that the global dynamics is linear because you suppress the nonlinear terms. And so we are left with this, plus boundary conditions. And of course, here I will be interested in the periodic motion. And so I assume that the velocity and the pressure perturbation is proportional to the some periodic function of time. Then you put this and you get this new term here. And so, in fact, these equations are the equations which govern the inertial modes in some on some incompressible fluid in some container. So that's the general problem. I will skip on their properties. They are orthogonal. They are low frequency modes, just like the waves actually. And just like the gravity waves. So these two set of waves will mix, and they have mathematical properties which have been studied, like they can make a complete basis in some containers. This has been proved. But the nice, or the a bit surprising thing is that they obey the same equation as the gravity modes. They obey also the Poincaré equation if you consider the pressure perturbation. Actually, Poincaré derived this equation when he was studying the stability of self-gravitating, rotating bodies at the beginning of the 20th century or at the end of the 19th century. So he derived this equation and then studied some peculiar cases. So this Poincaré equation, as I said, is a hyperbolic equation as far as the spatial coordinates are concerned. And you see that again here, we have a negative coefficient for the second derivative of the pressure with respect to z. So, in fact, the problem is mathematically ill-posed, which means that you can have singular solutions or no solution at all, or an infinite set of solutions. So let me, well, in the 5 minutes that I'm left with, I just say a few words about this problem, why it is ill-posed and why this is, in fact, this poses new problems in astrophysics. So just consider the well-posed hyperbolic problem. The well-posed hyperbolic problem is the wave equation, where you have here one space coordinate and the time. And you may have studied in small classes that if you make this change of variable, you introduce u and v, which are called the characteristic variables. You can reduce this equation to this one, and this is very easy to solve because f then is just the sum of two arbitrary functions of u and v, so x minus ct and x plus ct. And these two arbitrary functions are actually given by the initial conditions that you impose at some time. And this is the well-posed hyperbolic problem. However, the Poincaré problem is ill-posed because, in fact, it's just like if you impose initial conditions at t equals 0, for instance, I take this, and you impose a condition at some final time or some time later, new conditions. Or if you impose boundaries here on the so boundaries in this space-time diagram. And in fact, while this is ill-posed is that when you impose the initial conditions, then this condition will propagate along the characteristics like this. And in any point of this space, they will define the value of the solution. This is when this is well posed. And if you impose some boundary conditions like this, this final time, or some value which should be met by the function here, well, there is, in the general case, this value won't be compatible with the values that you have imposed on the boundaries. And therefore, you have a singularity, which could be just a jump in the function, or something which is more fundamental, as I will show in this case, in the case of the spherical shell. The case of the spherical shell, the characteristics, which are actually, they can be thought as the direction of propagation of energy. So the group velocity would be parallel to these. And so if you think of a particle or of a wave propagating like this, so its energy will propagate. And what you see if you trace these is that they focus on an attractor, on the periodic orbit of these characteristics. And in fact, this is a real singularity, which you can show that the density, the kinetic energy density of the wave is diverging when you reach the attractor. And you can see this when you solve numerically this problem. Of course, you cannot solve it if you don't have some dissipative mechanism, because we see here that it is singular. But with some dissipative mechanism, you can regularize the solution, make them derivable, or how do we say, square integrable. And you find something like this. You find that the kinetic energy or the dissipation concentrate around the attractor of the characteristics. And this is very interesting because the scale of these layers, actually, they are shear layers, oscillating shear layers, and the dissipation of the waves is concentrated in these layers. I think I will stop here because it would take me too far away, and I would need more time to discuss this, to do the following. So I will stop here. And if you have questions, so what we should remember, so you see that inertial waves and gravity waves, they are anisotropic waves, and the associated modes of these waves, when the waves are confined in some finite volume, then you see that the structure of the operator which governs the mode is very specific, and people who have analyzed for instance gravity modes in stars, as long as they assume that the stars were completely spherically symmetric, they could separate the variables, and they didn't see that. And so for many years, for decades, people have not realized that gravity waves actually are a solution of a singular problem when you neglect the diffusion process. And so, of course, stars are approximately spherical. So in many cases, it's not a problem, but when they are not, or when the waves are combined with inertial waves, then the problem is coming up. And inertial waves, they are much more sensitive to this problem. In fact, they just need to be confined to a spherical layer, and then their singularity is showing up. So I will stop here.